Well, hello. Continuing on talking about other types of aqueous equilibria, we're talking about solubility product constants. So calcium fluoride is insoluble, but it dissolves a little bit in water. So you put calcium fluoride in water, and it breaks apart into calcium and fluoride anions, respectively. The solubility product constant is going to be the calcium ion fluoride ion squared over the concentration of calcium fluoride. Calcium fluoride is a solid. We do not include that in the equilibrium expression. Therefore, it's just the ions. So the KSP is just the ions and the fluoride squared because there's two of them. So let's do this. Calculate the molar solubility of lead chloride, lead 2 chloride in pure water. So lead 2 chloride will break apart into lead plus 2 minus aqueous. And the solubility product constant, the constant you look it up or given to you is 1.17 times 10 to the minus 5. And it's just the lead ion times the chloride anion squared. Initially, we're going to have 0 of these, and the change the book uses S. I like to use the dollar signs because my S's look like 2's or 5's, I should say. So equilibrium is going to be S, and this is going to be 2S. So the KSP is going to be S times 2S squared equals 4S cubed. So that means that KSB, and this is 1.17 times 10 to the minus 5. So S equals 1.17 times 10 to the minus 5 divided by 4 to the cube root. And putting that in your calculator, 1.17e minus 5. Oh, that's minus 5 divided by 4 to the 1 divided by third power. And this means this is 0.0143. So the molar solubility is about 0.0143 moles per liter in pure water. So that's not very much. So that's why we say it's insoluble. It doesn't really dissolve that much. So let's go the other way around. The molar solubility of silver sulfate in pure water is 1.2 times 10 to the minus 5 molar. What is the KSP? So this is going to be 0, 0. The change is 2 molar solubility, equilibrium is going to be 2 molar solubility and molar solubility. So our KSP is going to be silver ion squared sulfate. So this is going to be 2s squared. S is 4 molar solubility cubed equals 4, 1.2 times 10 to the minus 5 cubed equals, throw it in our calculator, 4 times 1.2 e minus 5 to the third power. And let me sig figs to 6.9 times 10 to the minus 15. So that is our KSP, like that. So you can see silver sulfate even less soluble than lead chloride, so not very soluble at all. So now let's change it up. What do you do about a common ion? We've talked about the common ion effect with acids and bases. So the common ion for acids is hydrogen. So, but what is the molar solubility of calcium fluoride, in a solution that is 0.1 molar sodium fluoride? So the difference for this is the initial is 0. The common ion here, so the 2 fluoride here, the initial here is 0.1. So this changes the equilibrium. The change, we're still shifting right. We're still playing plus S plus 2S, and equilibrium is going to be solubility 0.1 plus 2 solubility. And our KSP is going to be calcium ion, fluoride anion squared, and that means 1.46 times 10 to the minus 10 equals molar solubility, 0.1 plus 2 molar solubility squared. And so what we can do, we can apply the discount small approximation there, and so then this approximately is molar solubility 0.1 squared, which is molar solubility times 0.01. If you divide both sides by 0.01, you will get 1.46 times 10 to the minus 8 is the molar solubility. So this one is pretty simple and straightforward. So this is what you do for the common ion, is you include the common ion in the equilibrium expression here in the initial conditions, just like we did with the combinations of acids. So why don't you try this for calcium fluoride? Hopefully you're seeing that you can manipulate it this way and not even needing a calculator. You could go through and calculate it out. I was hoping you would do it symbolically like that. So, and in general, not a compound with a strong base or weakly basic anion increases with the increasing acidity. Okay, so what does that mean? This is Le Chatelier's principle. So, remember when I told you I want you to memorize the strong acids? So strong acids, HCl, HBr, HI, HNO3, HClO4, H2SO4, but this is the first hydrogen only. And this means then that Cl minus, Br minus, I minus, NO3 minus, ClO4 minus, these do not react with hydrogen. Everything else will. So if any of these will react with, these will not react with hydrogen. So, and determine if it's more soluble in acidic solution than basic solution. So barium fluoride. So think of this as barium plus 2 fluoride minus. And the question is, will H plus react with barium plus 2 or F minus? And the answer is yes. H plus F minus will form HF. I should be able to go back and forth. And we know that because F minus is not one of these ions. Okay, so if you memorize those and the fact that they will not react with H, you know that F minus will react. And so this relationship, H plus F minus equilibrium for HF, look at this, and let me delete that. So that means F minus is consumed. And if we have this relationship, BaF2 in equilibrium with barium plus 2 ions plus fluoride anions, if we have the fluoride anions go down, we will shift right by Le Chatelier's principle, and more BaF2 will dissolve. So, and because of this, so this is more soluble. Is this more soluble in acid? Yes. Barium fluoride is more soluble. And the reason for that is what I said, because the fluoride anion will react with acid, the acid and the hydrogen, and then it will consume the fluoride anion to form hydrofluoric acid, and that will cause a shift right in this equation and more I should put a 2 there. More fluoride will dissolve, more barium fluoride will dissolve, so the solubility will increase of barium fluoride in an acidic solution. So let's look at B, silver iodide. Iodide happens to be one of these ions here that do not react with hydrogen. Therefore, will this be more soluble in acidic solution? This one is no, because the iodide is not going to react. So it's not going to react, therefore it's not going to be any different in an acidic solution or a basic solution. Then I'll do this in red, for calcium hydroxide, H plus, the same thing, will acid react, that's an ugly looking acid. Will acid react with calcium plus 2 or OH minus? And the answer is yes. H plus OH minus makes H2O. So putting calcium hydroxide into acid will react. It will react and more hydroxide will be destroyed and we will shift right. So calcium hydroxide solid, I should put 2. Calcium plus 2 aqueous plus 2 OH minus aqueous. This will cause the concentration of hydroxide to go down and we will shift right by Le Chatelier's principle. So this one is yes. So do you see this? That you have to look at a compound, determine if something will react with the hydrogen ion. And what will help you is to memorize the strong acids, understand what a strong acid means, and apply that knowledge that the chloride, bromide, iodine, nitrate, and perchlorate anions will not react with acid. But everything else will. And I'm not including sulfuric acid. It's a little more complicated. So the question of this is TSP, trisodium phosphate, more soluble in acid. So is PO4 minus 3, is that one of those in the box? The answer is no, it's not. So that means it will react in acid. So that means that this is more soluble in acid. So, okay. Another concept, so precipitation. We can use selective precipitation as a way to purify compounds. So there's a mineral called dolomite. Dolomite is calcium and magnesium carbonate. So you can take dolomite and you can heat it up to form calcium magnesium oxide, and you can crunch it up and throw it in water, and now you're going to get calcium and magnesium hydroxide in water. If you want, you can then take calcium, magnesium, and water. You can take that and you can react it, or even heat it up. You can just put a hydrochloric acid in it, then you'll form calcium, magnesium, chloride. Then you can add hydroxide to it. So the KSP for magnesium hydroxide is smaller. So adding hydroxide will get rid of the magnesium ions first. So this is an easy way to take a mineral like dolomite and make very pure magnesium hydroxide, and you can sell it to a company like Rolaids as a raw material. Then after a while you will get just pure calcium hydroxide, and you can use that for purified lime water, or you can bubble carbon dioxide through it and make calcium carbonate and then sell that to Xerox to make paper. So that's how chemically you can treat something, a raw material like dolomite, and turn it into two high quality useful materials for two different industries. Okay, so and let me talk about complex ions. I talked a little bit about it before, but there are some, this is known as crystal field theory or ligand field theory. Things will attach to a central metal atom, and you can form a ligand. This is how we get gold. So a couple ways we can get gold. You can just get it straight from the ground, get like a gold seam, and go with a pickaxe and go at it and find little gold flakes. That's one way. We've pretty much depleted the gold that way. You can also get it from riverbeds, because gold's heavy, it sinks to the bottom, so if you sift through mud, sometimes you find gold. you can do what they do in the Amazon is they take mercury and they pour it in and mercury is heavy, it sinks to the bottom, and they rummage that around mud in the bottom of the river, and then they take the mercury out, and then they take a blowtorch and they evaporate off all the mercury, and you're left with gold. That's a very bad way to do it. So please don't do gold that way. The way that we get gold in the United States is similarly, we find rocks that are pretty heavy in gold, and then we crunch them up and we get like what we call mud, some real heavy mud, and then we mix it with cyanide. We put cyanide into it, and the cyanide will leach out all the gold from the materials, and then we take that solution and we boil it off, and then we get the salts, and then we reduce it further, and we can get gold that way. So, but if you look at this complex ion, so we have silver complexing with water, and with two ammonias form silver ammoniated complex. And the Kf, the formation, is 1.7 times 10 to the 7th. So this is huge. One of the things I like about these is like whenever I'm doing equilibrium, it's so small, they're so tiny numbers. At least now we're actually making something. And so here are the formation constants for several things, and you can see that the cyanides are quite big. So do you have gold? I guess we don't have gold cyanide, but copper cyanide is 10 to the 25. So you can see that some of these numbers are quite large. So, and the various, some things are better ligands, and the cyanide happens to be a really good one, and it binds to our hemoglobin. Oh, we see here mercury cyanide. Mercury cyanide is 10 to the 41. So, see, that's really, really strong. So that's why cyanide can be so dangerous, as it binds to our iron and our hemoglobin very well. Okay, so let's do an example with these complex ion formulation. We have 200 milliliters of something that's 1.5 times 10 minus 3 molar in copper nitrate mixed with a 250 milliliter sample that's 0.2 molar in ammonia. After the solution reaches equilibrium, what concentration of copper plus 2 aqueous remains? So I'm just taking these. So if you take a 200 milliliter beaker, which is 0.0015 molar in copper plus 2, and a 250 milliliter beaker, 0.2 molar ammonia, you mix it together, and then you can do the concentrations by M1V1 equals M2V2. This is what you get. So I'm not going to go through how to do that. I've set this up for you. I set this up right now, so it's nice and easy and ready to explain. So here is our initial conditions, and the idea here is that we shift almost entirely to the right. So the copper basically is almost zero, and we shift all the way to the right, and the ammonia doesn't really change that much, and the copper complex is there. So when we solve this equilibrium expression, so the Kf is going to be product copper NH3 plus 2 concentration over copper plus 2, that's copper, and NH3 to the 4th power. So plug in the numbers. Oh, well, actually, we're solving for copper plus 2, so I can just go ahead and put the Cu plus 2. This is equal to Cu NH3 4 plus 2 concentration over the Kf times NH3 to the 4th power. That's a 4. So let's put it in there. It's pretty much all going to shift right. So 6.7 times 10 to the minus 4, all over 1.7 times 10 to the 13, big number, times 0.11 to the 4th power. So let me put that in my calculator. So putting that in my calculator, so I get is 2.7 times 10 to the minus 13 molar. So that's very, very small. So basically there's no free copper ions in the solution there. They're just tied up in with the ammoniated complex. So, but I like these. These are kind of fun because they shift all the way to the right. You finally actually make something. Some like where you're doing the acids and bases, almost nothing ever happens. Here, it's actually making something, which is kind of cool. And they're really pretty. If you do these in the lab, these are usually very beautiful. Those complex formations, especially with copper. It's a very blue, pretty blue color. Okay, so last thing I want to talk about are amphoteric metal hydroxides. So amphoteric means acts like an acid and a base. So aluminum hydroxide can act like a base because if you act with acid, you'll form aluminum ions. It can also act like an acid because if you put in hydroxide, it can form a ligand complex. So that's the last topic there, but I think it's kind of interesting that depends on the environment and things can act as acid or bases. Water's like that, amino acids like that, or even sometimes metal hydroxides are like that. So that's it for aqueous equilibria. Next topic we're going to talk about is thermodynamics part 2, where we learn about entropy and Gibbs free energy. So stay tuned for that coming up next.